All right, so I'm gonna try to record it myself, and then um, I'll see if I can post that to Canvas as we're going along, because I'm not 100% sure how to um, give approval for that at this point. All right, so why don't we do it that way? See if I can record. You're welcome. We'll see what happens. Hopefully it'll work. All right, so Kw, the ionization constant for water. Acid and base solutions are aqueous solutions. Aqueous solutions have some amount of H3O plus, some amount of OH minus, because as you saw in the notes, there is proton transfer that takes place in a sample of water amongst a small number of the water molecules that are present. What determines whether a solution is acidic or basic is dependent on the amounts of H3O plus and OH minus. Experiments have shown that for water itself, you have the one scenario where the amounts of H3O plus and OH minus are equal, and that's 1.0 times 10 to the minus 7th. And what they found was that when you have an increase or decrease in the amount of H3O plus or OH minus, you have the corresponding opposite effect of the other. Essentially, what you find is that H3O plus and OH minus are essentially inversely proportional to each other. And what that essentially means is that as one goes up, the other one goes down, and vice versa. They're inversely proportional to each other. One goes up by 2, the other goes down by 2, so forth and so on. So since you have essentially two variables that are inversely proportional to each other, when you multiply them together, they always come to give you the same value. And for water, that leads us to Kw, where Kw is equal to 1.0 times 10 to the minus 14, which was determined by taking the amount of H3O plus in solution and multiplying it by the amount of OH minus that's in solution. And whatever the amounts of H3O plus and OH minus are for a solution, they're always going to be equal to, when you multiply them together, they're always going to be equal to 1.0 times 10 to the minus 14th. Those are the two numbers. When they always multiply, they're always going to give you the same value. When you have two variables that are inversely proportional to each other, when you multiply them, essentially they always multiply to give the same value. Sorry, lost the slide there for a second. Let's see if I can go back. Okay, there. So they always multiply together to give the same value. So essentially, you can use Kw to find either H3O plus or OH minus. If you're given one and you're asked to find the other, you can do that. Now, you can't use Kw to find both, but you can use Kw to find one if given the other. Now, how do you do that? Well, essentially, what it always comes down to is, for example, if you want to find the amount of H3O plus, and this is just based on algebra, you take 1.0 times 10 to the minus 14th, and you divide it by the amount of OH minus. Because if you have Kw being equal to those two, if you have Kw being equal to the amount of H3O plus times the amount of OH minus, algebra would tell us if we divide both sides by H3O, if we divide both sides, by OH minus of that equation, then we can solve for H3O plus. So the amount of H3O plus would be equal to 1.0 times 10 to the minus 14th divided by the amount of OH minus. Conversely, if you're looking to find the amount of OH minus, again, you take 1.0 times 10 to the minus 14th divided by the amount of H3O plus. Okay, so if you're looking to solve for the amount of OH minus, you take 1.0 times 10 to the minus 14th and you divide that by the amount of H3O plus that's present. Now, one of the tricks is putting it into your calculator. I can't tell you exactly how to put it into your calculator because different calculators do it different ways in terms of putting in the times 10, the exponent, and the minus sign and such like that. So in the homework, which was returned to you on Canvas, if you haven't seen it yet, I returned the homework for chapter 10 via Canvas upload last night. If you take a look at the homework, if you are getting the right numbers, then you're perfectly fine. Essentially, your answers should always be somewhere between like 10 to the minus first power to like 10 to the minus 13th power. If you're coming up with an answer of like 1.0 times 10 to the minus 26th power, that can't be right. Your answers have to be somewhere between 10 to the minus first times 10 to the minus 13th. So unfortunately, I can't tell you exactly how to put it into your calculator. So if for some reason on the homework, if you've got those questions wrong and it came really down to a calculator issue, what one or two of you did, which was great, was you sent me a picture of your calculator and then I can sort of help you on a person by person basis. It's tough for me to sort of address how to put into everybody's calculator because everybody's calculator works a little bit differently. So it's a little bit difficult to do that. All right. Other questions about KW? So I'll just take a look at an example of one just to sort of make sure that we can solve. I don't think they're very difficult, but for this one, they want you to calculate the amount of H3O plus if the amount of OH minus is equal to, let's see what we got here. We've got 3.5 times 10 to the minus 4th molar. All right. So calculate the amount of H3O plus if the amount of OH minus is equal to 3.5 times 10 to the minus 4th molar. So again, whenever you're asked to sort of talk about and relate H3O plus and OH minus together, what has to come to mind right away is that you want to use KW. You're going to have to remember the KW formula. I'm not going to give it to you. You're going to have to remember it for the exam and such like that. So we'll remember that KW is always equal to 1.0 times 10 to the minus 14th, which would be equal to the concentration of H3O plus times the concentration of OH, sometimes it doesn't come out so well, times the concentration of OH minus, all right? So the concentration of H3O plus times the concentration of OH minus. So in this case, we're being asked to sort of solve for the amount of H3O plus. So we know that the amount of H3O plus, based on algebra, the amount of H3O plus is going to be equal to 1.0 times 10 to the minus 14th divided by 3.5 times 10 to the minus 4th. Okay. And if you plug that into your calculator, and I'll use my phone to help me, so I don't have to do too many things. Okay. So we've got 1 exponent 14 divided by 3.5 times 10 to the minus 4th. Hopefully you come up with an answer of 2.86 times 10 to the minus 11th. 2.86 times 10 to the minus 11th would be your answer. Okay. And again, if you're playing along and not coming up with that for whatever reason, if you understand the mathematics of it and just having an issue with the calculator, again, I can address that with you via email on a person by person basis. Okay. So that's essentially how to solve KW problems. And again, if you were looking to find the amount of OH minus, then essentially you would just sort of do the opposite. Do 1.0 times 10 to the minus 14th divided by the amount of H3O plus. All right. So that was sort of the one question that was sent in. I'll open it up to other questions about any of the topics that we've discussed so far. If you have any questions about them, if not, then I'll talk about a couple different things that might be causing a little bit of struggle. Okay. All right. So let's talk a little bit about one of the topics that usually gives a little bit of trouble, and that's a little bit about buffers. So the main idea behind a buffer is you have a solution that resists a change in pH when small amounts of acid or base are added to it. That's really the main idea behind a buffer solution, that you have a situation that if you add small amounts of acid or base to this solution, it prevents the pH from changing. Because in theory, if you add acid, what should happen to the pH? The pH should go down. In theory, what should happen if you add base to a solution? The pH should go up. Buffers sort of prevent that from happening. Now, how do they prevent that from happening? Well, there are essentially two components to a buffer. The first is you got to have an acid component. What's the main idea of the acid component of the buffer? It's going to react with added base. Okay. So the main idea of the acid component of the buffer is to react with added base. And by doing so, it prevents the pH from increasing. So that's one component of a buffer that you absolutely have to have. The second component of a buffer that you absolutely have to have is a base component. What's the purpose of the base component of a buffer? Well, the base component of the buffer is to react with added acid. And when it does so, what is it doing? Well, it prevents the pH from decreasing. Right? Because in theory, if you add acid to something, what should happen to the pH? The pH should go down. So for a buffer solution, you have to have these two components in order to have a buffer solution. Now, as I talked about in the notes, there's an inherent issue when you mix most acids and bases together. And that inherent issue for a buffer is the fact that most acids and bases react with each other. And when they do, their identities change. Because in theory, when you make a buffer solution, you want to add the acid component, you want to add the base component, but then what do you want them to do? You want them to sit there and wait. You want them to stay as they are, and you want to have them sit there and wait. Wait for acid or base to be added. If they react with each other, that's a problem. Because if their identities change, then they're no longer around to be the acid and base components of the buffer. And that's an issue, so to speak. So how do we get around this issue? Is there a combination of acid and base that can be used that will essentially be added together, sit there and wait and not react with each other? And the answer is yes. As we talked about, we use an acid-base conjugate pair. We know from our discussions earlier in the chapter that conjugates differ by one what? Conjugates differ by one proton. You know, if you have an acid, the conjugate base will have one less proton. If you have a base, the conjugate acid will have one more proton. But when you talk about acid-base conjugate pairs, you talk about that they differ essentially by a single proton associated with them. In a buffer, if you use an acid-base conjugate pair, that's great because they won't react with each other. They will sit there and wait until acid or base is added, which is what you need. Now, the conjugate pair comes from two possible combinations. And the one combination that we focus on in this course is the weak acid and salt, which provides the conjugate base. The other combination would be a weak base and a salt, which provides the conjugate acid. We mention it in the notes, but in reality, the textbook doesn't even glance at it any further than mentioning it. So we can almost put it to the side, so to speak. But what we want to sort of focus on is the combination of a weak acid and a salt. And the purpose of the salt is that it's going to provide the conjugate base. And one of the things that we'll go over again tonight, which was went over in the notes, is why you need a salt to provide the conjugate base. Okay. The other thing to mention is that strong acids and strong bases can never be used to make a buffer solution. Why? What's the problem with a strong acid and strong base being used for a buffer solution? They're not going to wait for acid or base to be added. Strong acids and strong bases are going to react with whatever they're with. So they have no patience. You can think of it that way. They have no patience. So strong acids and strong bases have no patience. They're always going to react with what they're combined with. So they can never be used to make a buffer solution. All right. So the example that we talked about in the notes was the example of using acetic acid, CH3COH, and its conjugate base, CH3COO-. So as we talked about in the notes, the way that we would make this buffer is that we would take the acetic acid and we would place it in water. Let's take a look at that equation for what happens when you take acetic acid and you place it in water. So here's that equation. Now, first off, how do you recognize it as a weak acid? Well, essentially here, we're looking at the Arrhenius definition. Remember, Arrhenius says that an acid dissociates upon dissolving in water to produce H+. Remember, dissociation refers to the separation into what? Dissociation refers to the separation into ions. Okay, so look at my products. My products here are ions. However, the key ion that's present that tells me that acetic acid is an acid is the fact that one of the ions is H+. Now, we also learned in the notes that we can tell from this equation that acetic acid is a weak acid. And how do we tell that from looking at the equation? We tell that by noticing the double arrow. The double arrow tells us that for acetic acid, its dissociation is never full. Its dissociation is only partial. In other words, as some of it splits apart into ions, some of those ions recombine. It's like the seesaw, back and forth, back and forth, back and forth. So when we look at this equation, we could tell that acetic acid is not only an acid, but we can also tell that it is a weak acid. So that's to keep in mind as well. So here, we get a small amount of H+. So if we start with water, which should be around 7, except for sometimes in our lab, the pH should probably go to about 5. So essentially, this is the pH that we're going to maintain for this buffer solution. This buffer solution is going to look to maintain a pH of around 5. Now, the good news is that there is still plenty of acetic acid whole molecules for the buffer. Why? Because when I take it and I place it in water, only a small amount of it dissociates. And remember, for the acid and base components of the buffer, when you go to make the buffer and you're adding those components in, you want them to stay as is. So if we're adding acetic acid to make a buffer, we want it to stay as CH3COOH. We don't want it to change. So that's the good news. The good news is that I take it, I place it in water, and most of it stays as is. So that's the good news. But here's the bad news. The bad news is that there is not enough CH3COO minus for the buffer. Remember, the first step in making this buffer solution would essentially be to take the acetic acid and place it in water. But if you do that and nothing else, you don't have a buffer solution. Now, you might be saying, well, doesn't the acetic acid produce the other component of the buffer? It does. But here's the follow-up question. How much of that other component of the buffer does it produce? Does it produce a lot or a little? And the answer is only a little. The same rationale that applied to the fact that we only get a small amount of H+ also tells us that we also only get a small amount of CH3COO minus. So the reason why you have to add a salt as the second component for a buffer is because the weak acid or weak base itself does not provide enough of the conjugate. For our purposes, if we're focusing on weak acid conjugate base, the weak acid does not supply enough of the conjugate base for the buffer solution. So we use salts. Now, why are salts good to use? A couple different reasons. Most salts will not affect the pH, and most salts fully dissociate in water. So here, one salt to use would be sodium acetate, which has the chemical formula of CH3COONA. So the next thing that I would do is that I would add the sodium acetate to water. Now let's take a look at the equation for what happens when I do that. And I don't know why it's coming a lot thicker at that point. So yes, Na plus CH3COO minus. So I take sodium acetate, I place it in water. The two products are Na plus, CH3COO minus. The key product, of course, is the CH3COO minus. That's the other component of the buffer that I need. But now here's the question. How much of that do you get from the sodium acetate? Do you get a lot or a little? And the answer is you get a lot. What tells you that you get a lot? It's the single arrow. The single arrow tells you that when you take sodium acetate and place it in water, all of it dissociates into Na plus and CH3CO minus. So that's how I would make this buffer. I would add acetic acid to water, and then I would add sodium acetate to water to make this particular buffer. Now, and if you have questions, feel free to jump in, use the chat, whatever you need to do. Feel free to jump in at any point. Now, so once we establish the components of the buffer, how does this buffer respond? In other words, when I add acid and when I add base, how does the buffer essentially respond to that? So what we want you to do here, more than anything else, is we want you to be specific. And in order to be specific, we've got to identify the two parts of the buffer in terms of the acid part and the base part. And it's really straightforward for our purposes. The acid part of the buffer is going to be, let's see if I can write that again, the weak acid. The weak acid that we're using to make the buffer is going to be the acid part of the buffer. And then the conjugate base, which again is going to come from the salt. The conjugate base is going to be the base part of the buffer. So it's as straightforward as that. The acid part's going to be the weak acid. The base part is going to be the conjugate base. So if we add acid here, it's going to be reacted upon by the base part of the buffer. But let's be specific. What's the base part of the buffer here? The base part of the buffer is the CH3 COO minus. That's the base part of the buffer. And that would react with added acid. Now, when we add base, what part of the buffer is going to react with base that is added? It's going to be the acid part of the buffer. Now, a common mistake that students make is that they say the acid part of the buffer is the H plus. No. And think about it. Why can't it be the H plus? Because if you change the amount of H plus, what else is also going to change? The pH. And what's the function of a buffer? The function of a buffer is to react or to maintain the pH. So it can't be reacted upon by H plus. It's got to be reacted upon by the acid part of the buffer. And the acid part of the buffer here is CH3 COOH. That is the acid part of the buffer. All right. So let's do, because I know the homework question wasn't that great in terms of looking at maybe something that I would be more inclined to ask you. So let's take a look at a different example. So let's look at a buffer composed of, let's see the example here, they give us H3PO4 and NaH2PO4. And along with that, let me give you a couple of equations. Here's the first. And then here's the second. All right, so here's, from my perspective, to answer what we're about to talk about, here essentially is all the information that you will need. So, question A, what type of buffer is this? Now, essentially, this is a giveaway question because even though there are two types of buffers, and that would be weak acid conjugate base and weak base conjugate acid, we've said in our discussions this evening, and you, as again, you can tell from the notes as well, that we really only focus on one type of buffer. Now, in case you forget that, how would you answer this question? Well, what I would do is I would go to the equations, and I would look for something that is weak to tell me whether that substance that I'm being used to make that buffer is a weak acid or weak base. Because then essentially I would know what type of buffer I'm dealing with. So what I would do here is I would look at the first equation. The first equation talks about something that is weak. H3PO4 double arrow, H plus H2PO4 minus. The double arrow indicates, the products are ions. So partial dissociation. And since one of the products is H plus, it tells me that, of course, H3PO4 is what type of substance? It's an acid. So H3PO4 has to be a weak acid. So what type of buffer are we looking at here? We're looking at a weak acid slash conjugate base buffer. And again, if I didn't remember just sort of the ideas of our discussion, I would know that to be the case because of the first equation. That tells me that H3PO4 is behaving as a weak acid in water based on the Arrhenius definition. So that's letter A. Letter B. What is the purpose of the NaH2PO4? And we want you to be specific. Why is it needed? What is the reason for it being there? When I'm making this buffer, why am I adding H3PO4 and why am I adding NaH2PO4? So again, this goes to the idea of salt providing conjugates. Because again, if we go back to the first equation, The fact that H3PO4 is a weak acid in terms of making the buffer is a good thing, because there's still plenty of whole molecules of it left for the buffer solution. The drawback is that, yes, it will produce some of the conjugate base. And actually, when I meant to, in the question, when I meant to say NaH2PO4, let me just change that a little bit to make it H2PO4 minus. This way, it's a little bit clearer, the question. So yeah, let's make it buffer composed of H3PO4 and H2PO4 minus. Okay. So the nice part is that, yes, it does produce some of the H2PO4 minus for the buffer solution, the conjugate base part. But again, how much of that conjugate base part does it produce? A lot or a little? And it only produces a little. Again, the fact that H3PO4 is a weak acid means that it only produces a small amount of the conjugate base. So let's look at the second equation. When I take NaH2PO4 and place it in water, the two products are Na plus and H2PO4 minus. Of course, the key product that we're interested in is the H2PO4 minus. How much of that is produced from the NaH2PO4? A lot or a little? And the answer is a lot. And what tells us that a lot is produced is the single arrow. The single arrow tells us that this substance, which is a salt, it's okay if you not recognize that totally, it's fine. But what you should recognize here is that the dissociation is complete. The dissociation is complete. So, what is the purpose of the NaH2PO4? It's the following. It provides sufficient H2PO4 minus for the buffer solution. And the way we're being specific is we're just not saying it provides the conjugate base. We're specifically stating what that conjugate base is. Its purpose is to provide sufficient H2PO4 minus for the buffer solution. Why? Because the H3PO4 does not provide enough of it. Does not provide enough of it. So that's letter B. All right, letter C. And let's go back. Let's keep the annotations. And let's insert. All right, letter C. What part of the buffer reacts with added base? And again, we're going to want you to be specific. Okay. Oh, can you repeat how you know it's a weak acid? Sure, absolutely. Let me go back. So the way we know it's a weak acid, again, we're looking at this equation here. Okay. You know it's an acid because you take it, you place it in water, and one of the products is H plus. But the way you know that it's weak is because of the double arrow. The double arrow tells us that the dissociation is only partial. It's not complete. So one of the things you should be able to do, especially with the Arrhenius definition, is look at a substance given the equation You don't have to memorize which acids and bases are strong and weak. But if I gave you this equation of H3PO4 and said, is it a strong acid, weak acid, strong base, weak base, you should be able to identify this as a weak acid. Question about OH minus. If one of the product, now remember, for bases, strong bases will dissociate to produce a lot of OH minus, but remember, weak bases don't dissociate. Weak bases only follow the category of being Bronsted-Lowry bases. They are poor acceptors of protons from water. But if you had a weak base, and I'll show you this, go back on the bottom here. For example, ammonia is the classic example of a weak base. First off, the reason why you know it's a base, based on the Bronsted-Lowry definition, is because it behaves as a proton acceptor. The NH3 becomes NH4 plus, it's a proton acceptor. But in terms of knowing that it's a weak base, how much OH minus is produced when the water donates a proton to the NH3? A lot or a little? And the answer is only a little. And what tells you that is the double arrow. So if OH minus is produced, it's a base. The single arrow will tell you essentially strong base. The double arrow will tell you weak base. But remember, for weak bases, they're the only ones that don't follow the Arrhenius definition. They only follow the Bronsted-Lowry definition. All right. All right. So let's go back to letter C. What part of the buffer? You're welcome, of course. What part of the buffer reacts with added base? And we want you to be specific. So we know in general that the acid part of the buffer is going to react with added base. Which is the acid part of this buffer? Is it the H3PO4 or is it the H2PO4 minus? Remember, the weak acid is going to be the acid part of the buffer. So the answer here is H3PO4. So it's just not good enough to say the acid part of the buffer. We want you to be specific. So the answer would really be H3PO4. And then letter D, what part of the buffer reacts with added acid? And again, we want you to be specific. Okay. So in general, what part of a buffer is going to react with added acid? It's going to be the base part of the buffer. But again, we want you to be specific. So what's the base part of the buffer here? The base part of the buffer is the H2PO4 minus. That's the base part of the buffer. So, future reference. Yes. So So as I said, the buffer question in the homework is not really how I would ask you about it, because there were some things there that I think they should actually really change to make it clearer. If you could answer these four parts, like in other words, if I give you, here's the buffer, these two components, here's the equations, and if you understood how to answer these four questions, then when I sort of ask you about buffers on the exam, you'll have a good understanding of how to answer them. I would ask it definitely more this way, different than much different than the homework question, because as I said, and you saw it even in the grading, I didn't take off points or didn't even, grade, I think, part C. There are certain things that they ask there that I wouldn't necessarily ask in terms of a buffer question. So this is more like how it would be asked of you. And that's why I wanted to take the time to go over that this evening. All right. Yeah, buffers is not, buffers is one of the harder topics um, that you come across in the class. All right, other questions that anybody's come up with so far? Anything else to go over? One of the other things that I did want to mention this evening, talk a little bit about, was the idea of, and I always forget I gotta put the pen back on. Let's not do subtitles. All right. So one of the other things I wanted to talk a little bit about this evening was the idea of isomers. So hopefully you had a chance to start to take a look at some of the concepts in chapter 11. And next time that we'll do a question and answer session, probably later on in the week, we'll spend more time focusing on chapter 11, because you probably had a chance to look at all of it up to this point right now. But one of the things that I posted at the end of last week that hopefully you had a chance to look at was the idea of isomers. And the reason why I want to talk about it at this point is to talk a little bit more about branched alkanes and the way that we draw different structures and such like that. So in terms of alkanes, remember alkanes are hydrocarbons. Hydrocarbons are organic compounds that contain only carbon and hydrogen. And alkanes are hydrocarbons that contain only carbon to carbon single bonds. And as you saw in the notes, there are different types of alkanes based on how the carbons are connected. You know, you have continuous alkanes where all the carbons are connected in a row, one after the other, after the other, after the other, after the other. The way that I like to think about it in a practical sense is sort of like single file. You know, one after the other, after the other, after the other, after the other, like the links on a chain or even like a conga line. You can think about it that way. Then you have your cycloalkanes, where you still have all carbon to carbon single bonds. But if you think about the ends of the parent or the main chain, when you get to the end of the parent or main chain, that last carbon has a bond all the way back to the carbon at the other end of the parent or the main chain. So essentially you end up going around in what? You end up going around in circles. In the world of organic chemistry, we call that a ring or a cyclic system. Then we came across what are known as branched alkanes. And for branched alkanes, all the carbon atoms are not connected in a row. For your branched alkanes, you have two parts. You have the parent or the main chain, which is the longest continuous carbon chain that is present. And then you have your branches, which are carbon groups connected to the main or parent chain. Now you might not have had a chance yet to really focus in on branches and stuff like that. As you'll see, if you haven't already, there are 4 branches that we need you to know in terms of carbon groups in this course. You'll come to know them as methyl, ethyl, propyl, and isopropyl. And we'll spend some time in the near future talking a little bit about those as well. So you got 2 parts. You have your parent or main chain, which is the longest continuous carbon chain present. And then you have branches, which are carbon groups connected to the main or the parent chain. Now, In the notes, the example we first took a look at to illustrate the idea of branched alkanes were compounds that had the chemical formula of C4H10. And as we tried to explain to you in the notes, one of the ways to come up with a compound that has the chemical formula C4H10 would be to put the 4 carbons in a row. They have to be bonded to each other, and the simplest connectivity that you can have would be single bonds. And then, of course, we want to fill in the rest with hydrogens so that each and every carbon has how many bonds total? And hopefully by now you understand the answer is 4. At the end of the day, each and every carbon must have 4 bonds total. So if we fill in 3 hydrogens on the first carbon, 2 hydrogens on the second carbon, 2 hydrogens on the third carbon, and 3 hydrogens on the fourth carbon, that would give us 10 hydrogens total. And would that be an acceptable structure for C4H10? It absolutely would. You've got 4 carbons, you've got 10 hydrogens. So, and carbon has 4 bonds. No carbon has more, no carbon has less, which is great. Hydrogen, of course, should only have 1 bond. Hopefully you understand that as well. And just as sort of a note, what type of alkane would this be? This would be an example of a continuous alkane because all the carbon atoms are connected in a row. One of the things I wanted to talk about this evening was the idea of how do we come up with something different, truly different, that has the same chemical formula, but actually has a different connectivity. Something that's truly different from what's here. And the reason why I mention this is because a lot of times when I ask students about isomers, they would take this and they would say, okay, here's an isomer of the structure above. And the problem is, it's not an isomer of the structure above. All you have done, technically, is taken this expanded structure, right? This is expanded. And what type of structure have you made here? It's condensed. But at the end of the day, these 2 compounds are exactly the same. It's butane. This is the first one's butane, the second one's butane. They're not isomers. To sort of look to step forward for a second, remember isomers have the same chemical formula, but different arrangements of atoms. There's nothing different here between these 2. They're exactly the same. Students will also say, okay, here's another isomer. No, it's still butane. Now, if you remember back to the notes, what type of structure do we have here? This is a skeletal structure where you'd have 1 carbon connected to the second, connected to the third, connected to the fourth. It's still 4 carbons in a row. It's still CH3 connected to CH2, connected to CH2, connected to CH3. These are all the same. There's no isomers here. Here's another point I want to make. Sometimes students will say, okay, here's an isomer of the first structure. And my response is, no, it's not. What you've drawn here is exactly the same as the 3 structures above. Because one of the important points to keep in mind is that the carbon atoms don't have to be connected in a straight line to be in a row. All they have to be is connected to each other. So this is still 1, 2, 3, 4 in a row. And even if you go the other way around, it's still 1, 2, 3, 4 in a row. Still 4 in a row. So this is no different than any of the 4 that, or any of the 3 that I've drawn on the slide so far. So how would you come up with something that's truly different? Well, as we saw in the notes, the way to figure out how to come up with something truly different would be, and this really is one of the ways of doing it. You don't always have to change the length of the parent or main chain to make an isomer, but really a good way to come up with an isomer is to change the length of the parent or the main chain. Because in this case, when I make the parent or main chain 3, and notice 1, 2, 3, 1, 2, 3, 1, 1, 2, 3, 1, 2, 3. You know, all the different ways you can get of going 3, the longest carbon chain is 3. And then if I fill in the hydrogens, 3 on the left, 3 on the bottom, 3 on the right, and 1 in the middle. Four carbons, check. 10 hydrogens, check. Have I violated any of the rules of bonding? Does carbon have more or less than 4? Well, violation would be more than 4 bonds, but does carbon have more than 4 bonds? No, it's perfectly fine. And this structure here is absolutely different than the 4 that we've drawn previously. And what type of alkane do you have here? You have a branched alkane. Because if I circle my parent or main chain, which if you've gone through the notes, you know that's something that I really like to do, I notice that there's a carbon group that's not circled. And this the way I circled it going straight across, because again, if you can go straight across, go straight across. The carbon group that I've circled here, well, the way I've circled my main or parent chain, the carbon group on the bottom, that's a branch. So this is an example of a branched alkane. All right, so let's do an example, another example. So we've got C6H14. And let's see if we can draw some isomers. And, you know, if I was going to ask you to draw isomers, which I probably will, I wouldn't ask you to draw every single isomer for a chemical formula, because as you could probably imagine, the more carbons and hydrogens that you have in your chemical formula, the more that there are more isomers that are possible. So we would ask you to come up with some. So for this one, we'll come up with a few to sort of highlight some things. So for compound C6H14, let's see if we can draw some isomers. The way that I would approach the problem to start is keep it nice and simple. Take the 6 carbons and do what? Put them in a row. Put them in a straight line. Not very well. 1, 2, 3, 4, 5, and 6. And then fill in the hydrogens so that each carbon has 4 bonds total. Six carbons, check. 14 hydrogens, check. Carbon only has 4 bonds. Each carbon has 4 bonds, which is great. Again, what type of, just as for some clarity, what type of alkane have I made here? I've made a continuous alkane structure here. So that's definitely an isomer, one of the isomers of C6H14 that you could create. Now, how would I go from here? Well, one of the things, as I said, to do would be to change the length of the parent or the main chain. Remember, for a continuous alkane, the parent or main chain is actually the compound itself. So for C6H14, the way we've drawn it here, the entire compound is the parent or main chain. The point being is that right now there are 6 carbons in the main or parent chain. Instead of having 6 carbons in the main or parent chain, why don't we try to cut that down to what? 5. All right. So 1, 2, 3, 4, and 5. Now the question comes, all right, where do I put that 6th and final carbon? Now, there's a couple different places that you could put it. Just so that we're clear, the 2 places where you can't put it would be on either end. So here or here. Why? Because then the parent chain would no longer be 6. Sorry, the parent chain would no longer be 5. It would go right back to being what? It would go right back to being 6. So that would be exactly the same as the one that we drew. But basically, I can pick sort of anywhere else of the 3 carbons that are left and put the last carbon attached to one of them. And honestly, whether you put it up or down doesn't make a difference. And then I would fill in the hydrogens. 3 here, 1 here. If I go to the bottom, I'm going to put in 3, 2, 2, and 3. And 6 carbons, check. 14 hydrogens, check. Is it different than the one that I drew above? Absolutely. What type of alkane are we dealing with here? Just so that we make reference, this is an example of a branched alkane. And it's another possible isomer to come up with. Let me show you one more. Could you reduce the length of the carbon chain even further? I mean, could you reduce the length of the parent or the main chain even further? Yes, you could. You can go from 5 to 4 and put in the other carbons, in different ways to come up with other isomers. But I want to show you that there's another isomer I can come up with where I leave the parent chain at 5. Where could I put that 6th carbon that would actually give me something different than the one that I just drew? And what I want to illustrate here is that you don't always have to change the length of the parent chain to come up with an isomer. As the chemical formulas get larger and larger, there's more isomers that you can come up with in keeping the parent chain the same length. Here, to come up with something different than the one before, I could put my last carbon there. If you think about it this way, you have CH3, CH, then you've got a CH3 at the bottom, and then you've got CH2, CH2, CH3. Let's fill in the rest here to see if we truly have something different. Six carbons, check. 14 hydrogens, check. Each carbon has 4 bonds, great. What type of alkane are we dealing with here? We're dealing with a branched alkane, okay? Is it different than the one I just drew above? And the answer is yes. Because if you look at it here, CH3, CH2, CH, and then the CH3 on the bottom. And if you go from right to left, any different direction, so to speak. And again, if we want to circle maybe we should also circle the main or parent chain, which might help as well. If not now, but definitely for future reference. Okay. So we get a little further, we'll notice here that this carbon group is actually attached to carbon number 2. When we get a little bit further on, you'll understand that this carbon group right here is actually attached to carbon number 3. What you should definitely see for now, if you put the pieces of the puzzles together, is that these two structures are different from each other. But one thing you couldn't do, in a sense, would be to you couldn't have put that last carbon over here. Because if you put that last carbon over here, it would actually be exactly the same as this structure here. Because if you would have done that, left to right and then right to left would have given you the same thing. But when I put the last carbon in the middle of the 5, that actually gives me something different than the one that I just drew above. So the point here is that you don't necessarily have to find the chain. You don't necessarily have to change the length of the parent or main chain to come up with an isomer, especially when the chemical formulas get a little bit larger. The last thing I'll mention, and then I'll open it up to any final questions if anybody has, is that keep in mind is that you really want to look carefully for the main or parent chain. Because there will be some instances where the main or parent chain would not necessarily be drawn straight across. And one of the things about organic is you really have to do your diligence to make sure that you find the main or parent chain. Sorry about that. Okay. So if you take a look at the example here, one of the biggest mistakes that students will make is that they'll say the parent or main chain here, this is an example of a branched alkane. And what they'll say here for a mistake is that the longest continuous carbon chain is 1, 2, 3, 4, 5, 6, just by going straight across. In fact, the longest continuous carbon chain here is 1, 2, 3, 4, 5, 6, 7, 8. When you're dealing with these branched alkanes, and especially as it pertains to naming, which you're about to see in the notes if you haven't looked at it already, is that you really have to do your diligence to make sure that you properly find the main or the parent chain. Because remember, it doesn't have to go straight across to be in a row. All the carbons have to be is connected to each other. So for this example here, the parent or main chain would have 1, 2, 3, 4, 5, 6, 7, 8 carbons long, and not 6. If you just would go straight across, blindly go straight across, in this example, you wouldn't come up with the correct main or parent chain. So that was sort of the last thing I wanted to mention from myself this evening. All right. Does anybody else have any questions? Anything they'd like me to go over at this point?
I have a question.
Sure, go ahead.
In your previous slide with the isomers, I know this is the next topic, but could you just name B and C, like the two different ones?
Yeah, absolutely. So this one right here would be known as 2-methylpentane. So as you'll see, if you haven't had a chance already, the first thing we do is we name the parent or the main chain by using essentially the continuous alkane name. So 5 carbons in a row with all single bonds would give us a parent name of pentane. Step 2 is that we want to number the carbons in the main or parent chain, starting from the end closest to a branch. So in this example, there's 1 branch. So there's 2 possible ways to number the carbons in this example. It would be 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. the idea is to start at the end closest to a branch. So the only correct way to number the carbons here would be as follows: 1, 2, 3, 4, 5. So that's where the 2 comes from. And then in terms of the branch, what do we call CH3 as a branch? As you'll see, CH3 as a branch is what is known as methyl. So in front of the parent name, you give the names and locations of branches. So in front of the pentane, you would have 2-methyl pentane. So that would be the name for the second one. For the one down here, it's still 5 carbons in a row. So the parent name would still be pentane. But in this case, it's whether you number it from left to right or right to left, the branch is still attached to carbon number, whether you go from left to right or right to left, the branch is attached to carbon number 3. So in this case, you would have 3-methyl pentane. And that's another sort of hint that they're isomers of each other because their names are different. You know, for the second one here, B, you have 2-methyl pentane, and then on the bottom one here, you have 3-methyl pentane. So that's how you would name those.
Thank you.
Another question came in. Let me go back to the KW one for a second with the calculation. So here's the thing. When you're working with negative exponents, essentially the only time you could sort of add the exponents to come up with the exponent for the final answer is if the coefficients are the same. In other words, if you have something like 1.0 times 10 to the minus 14 divided by 1.0 times 10 to the minus 4th, the coefficient is still going to be 1.0, and then the exponent would have to be 10 to the minus 10. And the way you would get that sort of is to sort of take 14 and subtract from that 4, and that would give you minus 10. But if you look at the example here, the denominator, the coefficient in the denominator is larger than the coefficient in the numerator. So what that means is that essentially you can't do that simple addition of the exponents, because the question is, why is the exponent here minus 11 and not minus 10? And the reason why is because the coefficient in the denominator is larger than the coefficient in the numerator. So when you actually do the division, it sort of looks like the exponents don't add up, but they actually do. Because if I take 2.86 times 10 to the minus 11, and I multiply that by 3.5 times 10 to the minus 4th, which I just did to check, I get 1.0 times 10 to the minus 14. So that's why you really want to trust and use your calculator. Now, if you had the coefficient in the numerator being larger than the coefficient in the denominator, then you could sort of use to subtract the exponent idea. But listen, here's my advice: use the scientific calculator. Because when the coefficient in the denominator is larger than the coefficient in the numerator, the exponents don't look like they add up correctly, but they actually do. So the correct answer here is definitely 2.86 times 10 to the minus 11, and not 2.86 times 10 to the minus 10. All right. So hopefully that answers that. And it just has to do with the fact that the coefficient in the denominator is larger than the coefficient in the numerator. So that's why the exponents don't look like they add, but they actually technically do. If you work backwards and multiply 2.86 times 10 to the minus 11 by 3.5 times 10 to the minus 4th, it multiplies to 1.0 times 10 to the minus 14. Other questions about any of the topics so far? All right. So I appreciate you taking your time out of your evening to join and hopefully clarify some things for you. So just to look ahead a little bit. So All the notes for chapter 11 have been posted to Canvas. They were posted last night. And the homework for that is due on Wednesday. We'll post some material for chapter 12 later on in the week, but basically right now you have all your material for the first exam. As it says in the syllabus, the first exam covering chapters 10 and 11, which will be on Monday. So I'll try to schedule another time for later on this week to do another question and answer session, so that if you have questions dealing with other parts of chapter 11, which you might not have gotten a chance to look at yet, we can spend some time looking at those. So that's a little bit about the plan going forward. The chapter 10 homework has been returned to Canvas via uploads. Take a look at that. And I'm starting to take a look at lab reports as well, especially for experiments 1 and 2, which should have been due on Friday, but I put the wrong date. So technically they're due today. So a lot of you've gotten them in already. So hopefully we'll get them back to you in the upcoming days. All right. Any last minute questions? And hopefully the video worked, and I will try to post it to Canvas in a little bit. Hopefully everything would have worked. All right. Any questions? All right. Stay well, everybody. If you have anything in the meantime, let me know, and I will see and talk to everybody soon. Have a good rest of your
Thank you.